Welcome to Progenesis webinar, session number 18. Today's topic is embryo selection with artificial intelligence. We are very pleased to have a panel of experts on AI, artificial intelligence. We have with us Dr. Alejandro Chávez Badiola. He is the medical director at Embryo Ranking. We have Oleksii Barash. He is the IVF lab supervisor at Reproductive Science Center of the San Francisco Bay Area. And we have recorded a third participant who is David Silver, research fellow at Embryonics. And because of that time difference, he's in Israel, it's 11 hours difference, so we have recorded him. And we're gonna try to make him live during the webinar. Thank you so much for attending the webinar, for your participation. We're gonna start the first presentation from Embryonics. Riley is gonna put that presentation and then we go to the next speaker. And we have with us now Embryonics.
Welcome. We are presenting today a novel algorithm to predict embryo implantation probability using IVF time-lapse imaging of developing embryos. This research is the result of a collaboration between the Clinic of Reproductive Medicine, Nadia, Professor Alex Bronstein from the Department of Computer Science at the Technion, and Embryonics, a startup company funded in part by the Israeli Innovation Authority. In vitro fertilization, the natural fertilization process is replaced by a manual one, where the sperm is used to fertilize the egg outside of the human body. Prior to transfer to the uterus, embryos are assessed manually by embryologists. This process attempts to select for the most viable embryo in order to maximize the probability of successful implantation, a necessary step on the path to a successful pregnancy. The grading of embryos has not evolved much in the 40 years since the invention of IVF. Morphological and morphokinetic events are manually recorded and various scoring systems are used to predict implantation. This process is labor-intensive and highly subjective and conveys poor success rates, averaging at 30% globally. Most previous attempts of using data-driven methods for time-lapse video processing were focused on predicting known morphological features, blastocyst formation, or the embryologist grading itself. These approaches are suboptimal as they rely on scoring systems that are inherently subjective and assume that historically defined metrics best correlate to implantation prediction. UBAR is an algorithm designed to improve the success rates of IVF by accurately predicting the probability of implantation from videos of the developing embryos. For the development of the algorithm, more than 8,000 time-lapse videos of embryos were used, approximately 300 of which had known implantation data, which was the ground truth for the model. UBAR is an end-to-end network designed to predict implantation probability. There are several key design principles to this network. Unsupervised methods were used to leverage all time-lapse videos through the use of an autoencoder. Training consisted of 8,000 embryo video files. Upon completion of this stage, videos are embedded as a time series of one-dimensional vectors. 4,000 embryos were then graded by an expert panel of embryologists. These were then used to initialize a network that, given a time series of embeddings as the input, predicts the embryologist's grade. This was done in order to prime the model to detect biologically relevant features. Subsequently, a new set of approximately 300 time-lapse videos labeled with known implantation data were used to retrain the prediction network and validate blindly on 10% left-out samples. Using tenfold cross-validation, predictions were generated on all of the videos without training on them. UBAR demonstrated state-of-the-art results when compared to any previous publication that we are aware of, and better than any expert embryologist involved in the research. Specifically, in any binary classification metric, UBAR significantly outperformed the embryologists. Importantly, both UBAR and the best-performing embryologists performed significantly better than random. For positive and negative predictive values, widely considered important clinical parameters, UBAR improved on the panel's performance by 12 and 29% respectively. Furthermore, the area under the ROC curve, which in this instance is a proxy to UBAR's ranking ability, was considerably larger at 82% compared to 58% for the embryologist's average score. This study demonstrates that our embryo implantation prediction model outperforms a panel of expert embryologists. The ultimate goal is for UBAR to be used as an assistive tool by embryologists to improve implantation success and therefore pregnancy and live birth rate in IVF. These results were achieved with a relatively small data set, A large and more balanced dataset should be used to further validate our approach. Introducing maternal clinical parameters, such as age and BMI, is likely to further improve prediction performance. In future research, we intend to report the prediction confidence and trace it back to the input visual content. This will increase the system's clinical viability. Thank you for your attention. Please contact us by email for any further inquiries.
Thank you so much. Now we will have Dr. Barash do the second presentation. Alex, you can start.
Okay. Can you see my screen?
Not yet.
Okay, share. Yeah.
Perfect.
Can you see it?
Yep.
All right. Good afternoon, everybody, and thank you for joining us for this webinar. In this presentation, I will share with you how machine learning is being used in the real world in our IVF lab. And I will try to skip as many technical details as I can, but I love it and I might get too excited. I have nothing to disclose. And in order to shine, machine learning needs several components. We need algorithm, we need computational power, and we need data. First of all, algorithm. You would be surprised, but most of the algorithms we're currently using were developed actually 30, 50, or even 70 years ago. And back then, computers were pretty slow, and researchers, they were hoping for the quick progress with AI, but their computers were about the same computational power as our TV remote controls. So this brings us to the second point, which is computational power. And we know the computational power getting cheaper and cheaper. And right now, for about $2,000, you can buy one single good GPU for about 14 teraflops of computational power. And the last component that we're actually getting just recently is data. We're getting data because we're using our EMRs. Data come from many different directions. This data stored, we can access it, and more importantly, this data is labeled, so we can connect outcomes of the treatment to the actual treatment, so we can run machine learning on this data. And in the past few years, we look at many different factors that can affect live birth rate. We look at maternal age, number of normal embryos, you name it. We basically look at everything we can. And because we look at these many factors, our data set was getting bigger and bigger. And at the end, as of today, we have a data set that have about 5.5 million unique data points and about 63,000 live formulas. So every time we need to add new data, everything got updated, and we can look at different angles on this data. But it was clearly not enough. So we thought, what if we can evaluate all the factors that we have, like all factors and all their interactions? And of course, for this, we would need machine learning. And otherwise, because it will be not humanly possible to do A to B analysis and compare, how one features interact with other feature. So about 2015, we started implementing some machine learning algorithms like classification and regression trees, like random forest and some others to our data set. And the data set actually was designed only for Ph.D. embryos. And right now we have about 14,000 Ph.D. embryos. And we have 320 features for each embryo. It's 145 features related to the IVF lab and about 170 features related to the clinical side, like medical history, patient demographics, drugs being used, and so on and so forth. So this is basically our data set. And the beauty basically about this data set that most likely in your lab, you'd have the same data. So you can pull the same data as we did and do your research on your side, because most likely you have this data. And overall, the data pipeline looked pretty simple. We input the data and we get predictions. But actually, all the magic happens on this slide. The most important step is feature engineering. It's the way how we try to extract the data, the knowledge from the data set. And we use many techniques like weight of evidence, target encoding, cluster encoding, Euclidean distance transformation, you name it. And it gives us a lot of features. But the most important features actually we add to our data set, there are the features that actually are based on domain knowledge. For example, if you have column with number of TPNs, you have column, for example, how many embryos you biopsied or froze. You can see, okay, I'm going to create a new column with usable blastulation rate. And these columns usually provide the best insight and the most important features for the data set. And sometimes it feels like a black magic because you create all these features and just give it to the computer. But at the end of the day, that's how it works. And because, as I said, the computational power right now is not an issue, we can use different algorithms because the algorithm look at the data in different angles. And then we can combine this algorithm in one final model by stacking the results of this algorithm, because we test each algorithm by itself. So then we can select the best of the class and then stack in the final model. And then this final ensemble of the algorithm produce our predictions. And we call this our predictions Reaper score. For us, it's just easier just to present it this way. So in order to create a robust model, the proper coefficients should be assigned to the features inside the algorithm. It's being done by computers, and this is how actually learning by computers, machine learning works. This means that features like age or morphological characteristics of the embryos can be ranked for the relative importance inside and be calculated. Like when we looked at feature affecting euploidy rates in embryos, we know for sure that maternal age is by far the most important features that affect euploidy rates. But also there's at least 12 other features that affect euploidy rates. And as you can see, most of these features, besides only maternal age, are lab related. So this might be the answer to the question why different embryology labs have different euploidy rates, because most of the features actually are lab related. And we did the same kind of analysis for features that affect our pregnancy rates, and we actually were able to adjust our treatment strategy and transfer fewer embryos, and now we're getting the same good clinical outcomes by transferring fewer embryos. Last year, we've done over 1,000 Ph.D. cycles, and our live birth rate is around 65%, while we're transferring 99% only one embryo. So I think this is Ph.D. itself and also machine learning and good clinical embryology practice all combined together to get this outstanding results. And as I said, we call our predictions Reaper score. It's designed similarly to credit score. It's basically one number to rule them all. It's just easier for physicians to have one number. It's easier to explain to the patients just this one number. And it helps not only to select the best embryo, but also to compare different patients and see what is this patient have chances, how big they are, and also compare different cycles, because picture doesn't have data about how many units of stimulation this patient have, what the age of this patient. And in many ways, we have patients who have euploid embryos from different cycles, so we can select the best embryo based not only by morphology, but also by features of this cycle, stimulation parameters, and so on and so forth. And of course, we develop a web-enabled application so we can give access to our physicians. So they just go online to the IVA Big Data site. It's ivabigdata.com. And this site actually have this data set with all the predictions. So physicians will go there, put the password, and enter the patient MPI. And in the same second, there's going to be selection what this patient have, what embryos, what genetic status of this embryos, and also the Reaper score calculated for this patient. And also this website has a public section when patients or physicians can come and see, let's say, what the chance to get euploidy rate based on age and based on number of eggs. And this is our data. It's the data that we update every year. We enter this data. And there's also a section when the patients or physicians can just put, let's say, 5 AB embryos and see how many embryos like this were transferred and what was the real clinical outcomes for this embryo morphology. And as all of this I said, we all actually just scratch the surface as machine learning. It's just new tools that can be applied to many, many other clinical decisions in IVF lab and on the clinical side. At the same time, each clinic should develop their own models because it's not easily transferable, this model, to other clinic. Partially because different clinics might have different data sets, but for the most part, it's possible to use a model in different data sets. It should be universal, ideally. And just in a few years, just to give you an overview, FDA approved over 50 algorithms in just 3 years. It's all commercial algorithms. And if you have a minute, just read these documents. I think it's interesting. It's outlined not just about regulation, but also the best practice, how to develop AI workflow and evaluate real world performance of the model. And we actually in IVF world actually behind at least 5 years from other fields like radiology, cardiology, because these people already develop algorithm, make a device under 510K section and sell it to companies. Like I just read yesterday about the company who scanned all the pathology slides, 25 million slides. I mean, it's just amazing and mind blowing. But for us, I just want to tell you that tools already there, people using them, they're all designed. All we need to do is just to transfer this knowledge as fast as we can and use them in our IVF world. And of course, I would like to thank our clinical and lab team, and thank you for your attention.
Thank you so much. Now we have Dr. Chávez Badiola. He's gonna start his presentation. I think you are muted.
Can you hear me now?
Perfect.
Fantastic. So I'm Dr. Chávez Badiola. I am Medical Director for New Hope Fertility Center in Mexico, and I am the founder of IVF 2.0, a company that is committed to introducing artificial intelligence into the world of reproductive medicine. So when we have patients, when we walk into the lab, every day we have to make decisions. But we also know that there is a huge difference between making decisions and making efficient decisions. Unfortunately, we're not always in the best mood. Sometimes we're tired, overworked, and that is going to bias our decision-making process. The advantage in using tools such as machine learning, artificial intelligence, is that we know that we're going to have a standard. Every day is going to be in the best mood possible, is not going to be tired, and that in itself is going to allow us to make more efficient decisions. Now, AI is pretty much that, is a tool to help in making decisions. And I believe that this technology could be integrated in almost every single step of the fertility process, from helping in making diagnosis, selecting the best treatment, the best stimulation protocols, the best time to retrieve the eggs, allowing us to assess the gametes, the embryos, helping us in choosing the best time to transfer an embryo, and even, as it was just suggested by Alex, allowing patients to have a better understanding about their chances of getting pregnant with certain technology, because definitely this will help in managing expectations and also allowing patients to understand whether they can afford emotionally, financially, the whole process. We have decided to focus on embryo selection for now. We would all like to have an accurate ranking, which is flexible, which can learn after 1,000 or even million embryos, and very important, that is a scalable model. We need science on steroids. We need artificial intelligence. And in particular, we're talking about machine learning. As it was just discussed previously, there are different ways of approach with mathematics a problem and use artificial intelligence, but not all artificial intelligence has a capacity to learn from larger and larger and growing databases. This is one ability of machine learning, and this is one of the reasons why we have decided to apply deep learning for the embryo selection process. More importantly, we believe that what embryologists need on a day-to-day basis is a ranking system. Just that, rather than just classifying an embryo as 5AA, 5BA, a system that will allow them to understand which embryo has the best potential according to what was just mentioned, a ground truth. And that's something that I'll talk about in a minute. So what we do is we take an image or a video, we apply standard artificial vision models to extract different features which are not identifiable by the naked eye under the microscope. And after collecting these features and adding some metadata, like patient's age, lab settings, including culture systems, the culture media that was used, then we extract all these features and then combine them so the computer can understand patterns related to ploidy or euploidy or aneuploidy. And this is Erica, our embryo ranking intelligent classification assistant. This is pretty much an embryo that you could see every morning in your labs. You could say it's beautiful, it's regular, it's horrible, but none of these words are scientific. So what we want to do is to extract more features than the expansion, the trophectoderm, the inner cell mass, which are just 3 features with many variables potentially. But we believe that there are more features that could give us a clue about the health of an embryo. Right now, we are assessing 94 features, which up to 275 variables each. So from this embryo, the computer sees this. Now, if you could have access to this image for each of your embryos, just tell me how many features could you extract? And how about now? Now, I can't recall the first image. The computer will recall every single detail for the first, second, third image, and many more images. And in this way, we're assessing just over 2.5 million trainable parameters to understand the chances that an embryo has to be euploid. Now, I think that we have to manage expectations. Can we, through AI, predict whether an embryo is going to become a baby? I'm not mocking anyone, but could you tell from an image from a 5-year-old boy whether he's going to make it into Cambridge or not? I think that that's way beyond the scope and the capabilities of the technology right now. We have to select what our ground truth is. And I think that fetal heart, live birth, or as much as these would be ideal clinical outcomes to measure, this is not realistic for videos and images. What we can learn is whether an embryo has a good chance to achieve implantation and being euploid or not. And this is what we're using our deep learning system, Erica, to do, and to assist embryologists in the selection process. How good is it? We know that we are not going to get 100% because even the biopsy is not 100% accurate. But we just want to make sure that whenever our chief embryologist is away on a holiday, or we have our most senior embryologist pregnant and going out for maternity leave, whoever is left in the lab will have an assistant that is at least as good as the best embryologist in the world. That's our aim, to have the best assistant for every embryologist anywhere in the world. How close are we to achieve this? This is a graphic from the paper we just published 10 days ago in RBM Online, where we are assigning tags random by chance to different embryos. Then we compare it against our two most senior embryologists and Erika. As you can see, Erika was way better at predicting ploidy than embryologists and chance. And it's not a surprise. Embryologists are not trained to predict ploidy based on an image. The important thing is when it comes down to clinic, how could this decision-making process helped by Erika could change decisions? This is a real case. It's also something that a figure that is included in the paper. This is a real case. Very young couple who had 6 beautiful looking embryos, and we asked all of our embryologists at New Hope to select the best embryo, the one embryo that they would transfer before they knew the outcome from the Ph.D. test. Every single one, 100% of them, chose embryo 2 as the embryo that they would have transferred. Now, for some reason, if you can see the before the last column, that was the worst ranked embryo. That was the embryo that Erika suggested had the least chance of being euploid and give a healthy baby. When the Ph.D. test came back, it was very shocking. It was the only aneuploid embryo from the test. And this is just a case. This is just to exemplify how Erika works and how it's meant to help and assist embryologists on a daily basis. The other issue when it comes to artificial intelligence, and there's a very recent paper, very nice, it was a Google paper, where they were trying to implement AI for an ophthalmology test in Thailand. It was a complete disaster. And the problem is that as good as the AI was, they never take into consideration the clinician's needs and their daily work. And I know that even if you have EMRs, there are a lot of tasks that embryologists have to do on a daily basis, from preparing dishes and taking the culture media out and taking a look into the embryoscope or assessing embryologists themselves. And the last thing that you want is another task. So we have also set to develop an interface and a web system that is very intuitive. And actually, if you have an EMR, you could ask a rank for your embryos with just one click. And of course, as we were discussing previously, the image of an embryo is not everything. We need to know more about the eggs and the sperm that are making these embryos. So in brief, as it was just suggested by Alex, AI, machine learning, is just a tool. It's a magnificent tool, a tool that we can access now that we have the technology, the computing power, and it would be a waste not to enter very quick into this new world to help and assist our embryologists and our teams to make the best decisions. Now, I want to thank our team of scientists, doctors helping us to develop Erika. And I know that there will be many, many questions. I can share the papers that we just published. And please contact me if you have any questions.
Thank you so much. That's a great presentation. I have a question for you. When you are, the first process I have, as I understand, when you are applying those algorithms to an AI algorithm is a discovery stage where you have to capture, you're not looking for any specific feature, you capture all the features that are available, and then you train the algorithm to start looking for the same features again and again. Is that how it works in AI?
If we are talking about machine learning, there are two different approaches, the supervised training and the unsupervised training. The unsupervised training is pretty much what I understand that you're suggesting, completely a black box. You just throw the images, you tell them the result, and then you expect the computer to find patterns. And the supervised training, you actually train the system to identify different things that could potentially be important. I'm just going to make an example. I think that, just an example, I think that the inner cell mass, the shape of the inner cell mass could be potentially related to prognosis. So I will let the computer know that I think this is something relevant, and it will extract features to complement what I'm saying. So it's going to be supervised. I'm telling the computer what it should be looking at. And then I associate this image, I tag this image, label this with an outcome. And then after the training, I validate. And after the validation, then I introduce a completely new set to test how good this algorithm is. And this relation of the validation results and the test results will let me know how robust my system is, how ready it is to be implemented in different settings, how good it is to generalize from what is learned in my lab, for example.
Very good. Alex, any comments on the training?
Now, in most cases in machine learning, we're using supervised learning because, unsupervised learning is usually cluster analysis. You just give the data and machine, you just say, I'm going to use the Euclidean distances. And, it's just going to give you some classes based on some algorithm. But the most powerful, it's all, something to do when you have labels. So you have labels, you can have outcomes, or you can do machine learning based on with neural nets and do backpropagation. But at the end of the day, the best way to do AI is to have labels. So you can teach machine how to achieve the goal. So you set the goal. This is the way how you can teach machine to play video games. You say your goal is to get this score. Bigger score is the better. Or your goal is to get through this tunnel. But this is how we learn actually, like as human beings. You tell your kids, you go this. If you hurt yourself, this is your feedback. This is your label. Don't touch it, basically. And the same with the machine. But with the machines, the beauty is they're not limited in power, computational power. Right now we have this computational power. In 10 years, we might have 10,000 more. And humans beings, we're very bad in these logarithmic scales. For us, 10,000 seems like, okay, it's like a million times. But in reality, like if you think about computational power, how fast it's growing, in 50 years, it's growing the same rate that if New York real estate would get cheaper at the same rate, you can buy everything right now for 10 cents. So, and with computational power, in many ways in machine learning, we don't know what we're looking for. We just give the machine the way to look at the problem at different angles and try different meta parameters, like different stuff. And everything right now, we can actually, you don't have to even input this parameter by hand. Let's say, you just say, here's the brackets, try these brackets and then other brackets, or you just program machine and then just sit and wait, drink your coffee. So yeah, that's how it's working machine learning.
Very good. So Alejandro, you mentioned that you can capture, or you have captured up to 2.5 million features on an image.
Yes.
What those features mean in biology? Do we know anything, or is it relevant to know what these features are?
We actually started with almost 40 million features, but if you consider that Google uses 25 million to classify the whole world, it was completely ridiculous, and we were risking overfitting considering the size of our data set. So we brought it to the bare minimum. And there are many, many features, like, for example, if we want to make sure that Erika is going to be able to offer same results regardless of lab settings, then it uses parameters such as the relation between the blastocele and the inner cell mass, and that in relation to the overall size of the embryo. And then the tough ectoderm, and it tends to count cells, but also finds patterns on how this is. And there are many, many things that I just don't understand what Erika is doing. We give Erika a guide, we give her a data set, label, and then we just test. So there are many, many things that I don't know. I wouldn't even be able to remember 100, so 2.5 million. I have no idea.
Yeah.
When we're talking about pictures, I mean, it's just when we see embryo, we see embryo. But when we give this picture to the computer see pixels, you know, black and white pixels. And for the computer, it's the same features we see, you know, like in tabular data, but it's just pixel number 1, this light intensity, pixel number 2. And at the end of the day, what computer sees, it doesn't see ICM. It says black pixel surrounded by the white pixels. And it should be a certain distance between black and white pixels. And this is how computer learns the pattern. For computers, embryo does not exist. It doesn't have consciousness. So for him, it's just black and white pixels. And also, in many ways, we have actually downsized the pictures because our camera can make a picture, you know, 2 million by 2 million pixels, but we give them size of like 300 pixels by 300 pixels. Like it's tiny postmark size pictures actually, and still computer can't figure out the data. In the future, with the computational power, we will be able to analyze all these millions and millions of pictures. And as was mentioned about Google right now, there is a recent paper, they're using billions of features, but they're trying to apply it to the natural language. So you can imagine in ICM of embryo how many features you can see with 10, 100, 20,000 features. But with natural language, it might be millions and billions of different accents, different words, different letters. So as far as we see right now from Google, they can prove that bigger data set and bigger computational power still produce not diminished returns. So we still get bigger returns, which basically says, if we're going to have more data, more pictures of the embryos, more videos of the embryos, and more computational power, we're going to get bigger results, better results. We still didn't get this S-curve, we plateaued. I think it just...
I absolutely agree with you. And my point, for example, suggesting that we cannot predict a live birth right now. I think that I completely agree with you. At some point, gaining access to big data, we will be able to tell a couple, listen, you have a fantastic chance of getting pregnant, but you shouldn't be traveling to South Korea right now. And why should I travel to South Korea? And then the computer will know that just because of the profile of the husband, there is a high chance that he will travel to South Korea at the right time, where North Korea has the biggest chance of sending a nuclear attack. So we shouldn't go to North Korea. So big data will not only be able to get closer to 100%, but also to influence the final outcome. And this is one thing that we're working on with Erika, to try and understand how we could influence the chances of an embryo of developing and reaching its full potential by changing culture media earlier or later, not changing it at all, phrasing earlier, later, the best time to perform a biopsy and to transfer, for example. So there's a long way to go, but the potential is there. And as Alex was saying, the tools are there. We just need to increase our data sets. We just need to broaden our minds and approach this in different ways.
I think also we have a potential about the data that we already have in different clinics. They have this data but don't use this data. Let's say time-lapse data. We can look at this data retrospectively and just use them. You don't have to produce the data for the future. You can, if you have somewhere the data in your hard drive, just find somebody who can use it.
Yeah, absolutely. So we have a question we have actually 2 questions from the audience and one on a chat form. One question that is, before I pass the mic to John will be reading the questions from the audience. There's one question that really calls my attention in the chat, which is mosaicism. This should be relatively an easy thing to solve in an embryo if you have such a high resolution image processing. What do you think? Is it something that an algorithm can capture a mosaic embryo?
Personally, I think that even though we have trained Erika against euploidy, I'm just going to make an example. Erika won't tell you if you have a high chance of a Down syndrome, because that's a perfectly looking embryo that will achieve an implantation. With mosaics, is very similar in the way that there are good prognosis mosaics and poor prognosis mosaics. Right now, Erika cannot tell the difference between those intermediate mosaics. It can tell from the extremes, but rather than trying to predict what is very challenging to predict right now, our approach again is to assist embryologists in the process. And this is only going to become more and more challenging, because if you call embryologists from different labs, just random, and you show them 10 mosaics, I can guarantee that at least half of them won't have a clue on how to rank them. And okay, this is 30% mosaic, but it's mosaic number 13 that is involved, and you have this one which is 40, but it's chromosome 1. So which one has a better chance? I have to make a decision. So do I go to the book? Do I go to my lab director? Do I go to the clinician, the geneticist? And Erika is able to rank and let you know automatically which embryo you should be selecting and which embryos are not to be transferred. And as I was saying, this is going to get more and more complex for embryologists when you'll have to introduce metabolomics and proteomics and many more information that is coming into the market. And if you tell me about the proteomics, the metabolomics, and the mosaic, believe me, the picture of the embryo is already out of my mind. So how am I going to integrate the morphokinetics, the morphology, and everything in between? So
Yeah,
this is the aim of Erika.
Yeah, I agree. Alex, any comments on mosaicism
You know,
detection?
I kind of gonna say just, I agree. And what we do right now, we're actually picking up very low hanging fruits. We basically, in very simple calculations, can go from 50-50 chance to pick up normal embryo to 70% to 80%, but it's just, the beginning. And this diminished returns on this curve, it's far, far away from today. So I think even, by doing this relatively simple, calculations in picture analysis or, data analysis, we already can achieve a lot without any actually, extra steps. So I think machines can see way better than we can see. They are expandable, they're scalable, and it's no way any human beings can compare to machine. And in the future, it's computational power getting cheaper with more data. I think right now we're getting actually to the tipping point when machines become better even in a VF lab in embryology. I don't think there's going to be any time return back to the normal evaluation as we did 5 or 10 years ago, because we're just not good at it. Each embryologist can see how many embryos, 1,000, 10,000 embryos. Like machine, you can feed the millions of the pictures to the machine, and with the outcomes, teach the machine on the millions of pictures. It's not possible with anybody on a human being. So, very good.
Let's go to the questions. William, if you can take the question on the PGTA and the algorithm.
Yep. So the question was regarding, does Erika, so they say that Erika appears to be trained and tested mostly using PGTA results. So how does this then extrapolate to pregnancy outcome? And have you tested the ability to predict pregnancy outcome through Erika?
Erika has been trained both on euploidy, prediction, and implantation. And we're working on the combination. Right now, Erika, what it does is, if you have PGT results, it will rank based on ploidy and the chances each embryo has to implant. So it will always put euploid embryos on top. If you don't have a PGT result, then it will report according to number one, the chance that Erika believes that this specific embryo has to be euploid. And after it has ranked in this fashion, then it will assess implantation potential. So it's a combination.
Okay, so I'm gonna take a break from the next question. So I have a question for you, Alex, about the repro score.
Repro score.
Repro score, very nice name, by the way. Yes. So the Ripper score use a variety of parameters to predict pregnancy outcome, right? It looks at
And
the
equality also.
yes. Um, what tell us a little bit about the Ripper score in terms of have you tried it with and without algorithm and compared the data? Did you do any blind study on that?
You know, we haven't done any blind study, but when we train algorithms, the way we train it, we divide our data in the training and test set. So we basically train algorithm on a train set, and then we give the algorithm completely random data. And then they compare what the algorithm predicted and just build confusion matrix and see what was, you know, right and what is wrong. So this is how we test it. And the way how we select embryo for the transfer, for us, almost 100% of our patients do PGTA right now. So we basically do 1,500 ychilas every year. Almost all of them are PGT. So for us, first of all, we'll deselect embryos based on the genetic analysis. And then from the remaining embryos, we'll try to select the best one. But based on our experience, honestly, probably 10 to 20% of the times we need to make a choice because most of the times it's pretty obvious, or we don't have enough embryos to select from, or it's just, you know, you have pretty obvious decision about, but I think it's the value of this tool also, it's just to set patient expectation so they will know what to expect. And, you know, as I said in my presentation, it's also possible to compare diploid embryos from different cycles because they're going to have different Ripper score results because they come from different environment. Because in this algorithm, we plugged, for example, how many follicles it was, how many follicles actually had what size, how, you know, all these features that are not possibly analyzed otherwise. And if we will just do pictures, picture doesn't have, you know, age of the patient. You have to do it additionally and combine. And we get to the point when all the data will be from different angle combined. I mean, I have some preliminary coding projects when we put the unstructured data, the data from patient charts. It's a huge amount of information and it's going to be used in future. It just, you know, we need to find the right approach how to use this unstructured data from progress nodes. And we have, you know, probably a dozen other ideas how we can improve this algorithm. So it's just the beginning. But for us, I mean, on everyday basis, it's nice. We can look at the, you know, predictions. We can see if we agree with or not agree. But most of the times, you know, you see, oh, why this embryo was 5BB, but, you know, it's got higher Ripper scores than this 5BA embryo. And you would see, oh, I know, because this embryo was from day 5 and this was from day 6. Or this embryo comes from this cycle where we stimulate 12 days, not 14 days, and so on and so forth. So most of the times, even the predictions are not, seems to be a little bit out of order. When we look at the details, usually the machine does better than people. So it's just for human beings, it's hard to analyze all these hundreds of features.
Yeah, so a main distinction between your perspective and Alejandro's perspective is that you were saying that this model is not transferable because you have to train the data and then.
No, I think it's transferable. I think it just will not be not 100% transferable. I think if I will just take random data from somebody else and just plug in my algorithm, it will be probably 5, maybe 10% less accurate than, but it's still going to be, you know, instead of being 80%, it's going to be 75 or, you know, 72, 73, way better than human being anyways.
Yeah.
I absolutely agree. Actually, that's pretty much what I was referring to, these tuning. Pretty much what we aim for is to create a very robust algorithm that is good wherever you put it, but it can learn from specific data sets and different lab conditions. And one example is the Embryoscope. Embryoscope is a beautiful machine, very nice algorithm, very elegant, but unfortunately when it was deployed into the clinic, their algorithms were not as good. And it came back with the fact that different labs were using different culture media, and different embryos grow at different rates depending on the culture media that you use and different conditions. So Erika doesn't disregard this. This is why we're including a metadata as patient's age. And when we set up a lab, we ask you, which kind of culture media are you using? Which is your preferred? And whenever you make a change, You have to let us know. It's not that it's going to make of your results a complete disaster, but if you're paying for a high performer, you want it at its best all the time. And this is what we do with the fine tuning and the quality assurance tests.
Is the algorithm based on images or time lapse or both? Can it handle both? Do you see any advantage of looking at a video versus looking at a static image?
My example is going to be terrible, okay? It can assess both images and videos, because strictly speaking, the time lapse is a series of pictures. Now, we have to focus our attention on, Erika is not trained to take the whole video from a time lapse. It takes sequences of images from probably the last day or so. My example is this: pretty much, I want to hire the best marathon runner in the world. And I have the chance to hire this runner anytime I want, except at the finish line. So I could hire this at the start. And what if I get this Kenyan guy that breaks his ankle? I lost. Why did I have to choose the embryo at the very beginning? Our bet is to choose from the lead peloton at the very last time, few minutes, few hours, and then choose the embryo from that perspective. So we can take images, we can take videos, and we're training Erika to be very flexible. Why we chose images to start with rather than videos? Because probably 80% of the labs in the world rely on images and regular microscopes. Very, very few have time lapse. And even those that have time lapse, most of them have time lapse just for a percentage of their cycles, for a minority of their cycles. New Hope in New York, for example, 6,000 cycles, collections a year, one embryoscope. We just bought 12, but that's a different story.
Very good. Alex, what is your opinion?
I agree that, in general, in machine learning, when we train CNN, convolutional neural network, and usually if we will take pre-trained, let's say Vitrolife has their network pre-trained on 100,000 embryos, right? And if I'll take their network and apply it to my data, it will be better to start from their network, even though it's absolutely different embryos. I can train this network better if I will just add my embryos to their network. It's kind of counterintuitive, but this is how machine learning works, because the machine learning can catch the general features already. So pre-trained network from some other labs or companies produce better results. And also time-lapse in general, I think this company just only now realized that they are not hardware company who produce time-lapse systems and actually software, because in a few years, they're going to be selling algorithms, not these boxes with the camera. And we have time-lapse, with the embryoscopes for 10 years. And the major breakthrough with AlexNet, which was developed by Alex Krzyzewski and Ilya Shutskever, was 2012, 2014. So almost 10 years ago, the technology was there with a major breakthrough. They just missed it. They should have done, this research by themselves 5-10 years ago. And I believe right now, when the people develop the algorithms, most of the people will finally see the value, not just with, these funny, nice pictures when you can have an IVF lab, but something tangible that you can sell, that you can improve. And I believe they will be able to sell more time-lapse systems, because right now there's actually real world case use for these systems.
Yeah, we have had an interview with Embryonics early on a couple of days ago. They were supposed to attend the webinar, but because of the time difference, they are in Israel, 11 hours difference, we decided to capture a small video where we have exchanged ideas. We have asked one of their researchers, David Silver, we asked him if he has compared his data with and without AI to see the differences. They are developing a similar algorithm. And here is the video and what he is saying.
did a very large retrospective study on thousands of embryos. We published on data that we collected a year ago that we had more than 8,000 embryos, and we tested on several hundred with very strictly defined known implantation data. And we didn't only compare it against ground truth results, which is obviously the baseline. This is the ground truth that we compared against. We collected from more than 36 embryologists scores for these embryos, and from any algorithm that is available to use on your own data, we've tested also against that. And yes, our results were benchmarked for the real data and against other baselines such as average embryology scoring, best embryology scoring, and other software. But as I must emphasize, all of these numbers are not meaningless, are very important, but unless there will be a data set that's the same data set that different people can test their algorithms on this data set, all those numbers are very weak. There must be, and we're always calling everyone else that's in the field to have a centralized data set, then so we can compare meaningfully all these metrics on.
That was a great point. Would you guys be willing to participate in a study where there is a centralized database of data that you can test your algorithm on?
You know, I think it will be definitely useful, but I think it's not going to happen like we're going to combine our data set. I think the more realistic would be if we can have some kind of like competition and just, you know, put the data set somewhere and analyze and do predictions, something like this, because I don't think it will be possible to combine, at least in this stage, just because of patient privacy and, you know, all other issues. And, you know, the major players right now, they're still, you know, competitors and based on how they want to, you know, get the market and share of this. But so I think it will be better to do competition than to exchange the data sets, because as far as I see, Vitrolife, they present this data about 100,000, 112,000. I mean, it's a huge data set, you know. I don't think they will be willing to share this data with, you know, researchers.
I completely agree with you. I think that.
But I would love to take it. I mean, if they would agree.
Yeah, I mean, we were just talking about this earlier on. I think that would be very good to understand and learn where we're standing. And then that would also be very good for potential clients. But I think that a lot of groups are going to be reluctant to this because this is a competition and I'm not going to share with you my data set, number one, privacy issues, but there's always a competition. And what if you're better than me? Am I going to lose some share of my market? And since this is mostly pushed by private companies and we're doing it, I have to make the best allocation of resources. And if this is not going to give me any potential benefit in improving my system, then I might be reluctant to participate. So we've had this experience. It was not taken very enthusiastically, as it was suggested by just now.
Yeah.
But I think that if we could have access to some federate training or even a data hub with blockchain, where the privacy was practically guaranteed, I think that we would all benefit from that. Now, going to the Vitrolife presentation with the hundreds of thousands of images, I just want to make a point here. As a clinician myself, if you present something that has a few thousands, I'm going to be impressed. I know how difficult it is to gather this much information. If you come with 100,000 and you published fertility and sterility, I'm not going to look into details, the methodology that is very complex jargon in mathematics that I don't relate to. I'm just going to believe what they're saying. Now, I think that we have to educate ourselves about how to validate and interpret and read AI. That specific presentation had a terribly unbalanced data set. And if you take the whole data set, and I think it was 80-something% of the embryos were discarded, they never got to the point of blastocyst. If you discard randomly the same amount of embryos, split by half their data set, you will get 94% accuracy for non-implantation. So no AI, basic mathematics and chance. So we have to be very, very careful about the data sets that are being used for training, validation, and testing. If you check how many embryos actually had a known outcome, referred as fetal heart, and that was their ground truth, there was, I think that it was just over the 10,000. Forget about the 100,000. I think it was
14,000. It was 14,000, yeah.
14,000.
Yeah.
It was 1/10 of the data set. So in truth, they should have trained against that. And when you look in further detail about their KIT score, the known implantation data, then the accuracy is a disaster. So yeah, we have to make an effort to better understand AI papers from now on, because they are going to inundate the journals. So we have to educate ourselves and make an effort to understand these papers.
Very good. So I looked at the presentation that you guys both have given. And when I look at the predictive value, negative and positive predictive value, it's still not there to say, well, you have, I mean, in any clinical test, you're going to need a 95% accuracy to be comfortable doing it. What does it take to go from an 80% positive predictive value, 71 accuracy, to what we really need? Or should we use this just as a score in addition of other things?
Like in our algorithm, we have about 0.8 accuracy, and AUC about also 0.8. It's not super great. I mean, I think it's to get to 100 or close to 100, I would say we need bigger data sets, first of all. We need to eliminate all the bias from the data set, so everything should be automatic, no human involvement. And I think maybe new algorithm, you know, if you can run, you know, light GBM on everything, not just, you know, on something. So basically we need more computational power and bigger data sets, I think, to get there.
Alejandro?
It depends on what we're aiming for. Right now, we aim to assist embryologists to select the best embryo, not to predict a heartbeat, for example. We know that 20% of the responsibility of implantation is related to factors that have nothing to do with the embryo. So the embryo is only 80% of factors. So even if I am 100% accurate at telling you that this embryo should implant, there's a 20% chance that the clinician will mess up or that the lining was not perfect. Now, we need big data for that. We need a different kind of algorithms, a completely different approach. But I think that it's not just a ranking. What we're doing with embryo selection, embryo ranking, is also a quality assurance system. If you're consistently getting top quality embryos according to a ranking, and you're having terrible results, then there is a good chance that you should be looking at something else. So there are different approaches on the way that you could use AI. As Alex was saying, this is a tool. You have to make the most of this tool. So 100% someday, but not now.
No, it's actually resonates what I was thinking. I was thinking if you want to have 100%, we need to grow embryos in the lab 9 months, not 5 days.
Sure. Should we look beside the embryo images, and should we look for other things?
Yes, and as I said, I have at least a few other ideas where this data can come from. And I definitely say there's a lot of usable and valuable data in there, not just pictures, not just tabular data. There are many other sources. And, you know, we're just scratching the surface, I'm telling you.
Yes. And would the algorithm be adaptable to a point that you can use any kind of data?
You know, with neural nets, they don't care. It's a pixels. They don't care. It's a pixel from the picture or it's a age of 45 in a data set, you know. For them, it can be anything. The neural nets, they just eat whatever you give them. And I think in the future, when computational power is going to be, you know, enormous, we can just throw everything there, get pre-trained networks from Vitrolife or whoever going to provide them, and just adapt it to our data sets. And I think it's not going to happen in 20 years from now. It's going to happen in the next 5, maybe less.
Alejandro, do you see a scenario where you can adjust in real time in medical practice, such as stimulation dose and other decisions of when to transfer and all these things based on AI applications?
Yes, definitely yes. As we speak, we're integrating Erica into more features of metadata. We are now working on integrating Erica into the prediction of the chances of a single sperm that was selected for injection and the egg. And definitely, as Alex was saying, it's going to be relevant, the total dose of FSH, where this egg is coming from. Is this coming from a good cohort, from a cohort of 30, 100 eggs, or just minimal stimulation, natural cycle? Is going to make a difference. I think that there is a good chance that with the resources that we currently have, we could see, as Alex was suggesting, a dramatic improvement within 3 to 5 years. We tried to do this with more data, and although we believe that it was impossible, we literally crashed our computers.
Absolutely. We are getting close to the end of the webinar. We're going to take some poll results. William, if you can get the poll and tell us what we found. Okay, let me read the results. So we have, William, you're there?
Yep, no, I'm here. John was going to do the poll.
Okay, John?
Yeah, I'm here, Dr. Barash. So question number 1 was, how do you currently select embryos before transfer? Embryo grade, PGTA results, mitochondrial, time lapse, or other. 89% of the audience, our guests, chose embryo grade. 82% was PGTA, 8% mitochondrial, time lapse 8, and 5 for others. Question number 2, are you willing to use any form of artificial intelligence to score your embryos? Yes was only 11%, and no was very significantly higher. It says 103%. I don't know how that's percentage-wise adds up. It's 114% for both questions, but the majority was no. No, they're not using any form of artificial intelligence to score embryos. Question number 3 was, do you see yourself using AI in the future? Pretty substantial number and difference. 97% of our guests said yes, and 16% said no. So yes, they will consider and see themselves using artificial intelligence in the future. Question number 4, are you using time lapse? 16% yes, 97% no. 97% no, they're not currently using time lapse. And the last question, question 5 is, are you interested in participating in a multi-centered spent media research project? 76% of our guests said yes, and 37% said no. So those were the questions, the poll questions, and thank you for letting me share those.
Thank you. Thanks, John. Thank you. So what strikes me in this poll is that the majority use embryo grade for selection, but also the majority wanted to see some sort of AI solution to select embryos. So there is definitely a need there for embryo selection. Before we wrap up the webinar, I'm gonna take your guys' opinion on the poll, and we're gonna release, I think we have released already the first poll. We're gonna release the second poll. Riley, if you can help us with that. Meanwhile, we're gonna take your opinion on the poll. What do you guys think?
I think, it's what I see. People barely use time lapse because it's expensive and didn't produce much value until, now basically. And I definitely see it gonna change. And AI, I think, people don't realize that they actually use an AI already by, sequencing, NGS is done by bioinformatics inside there, or in the mutual receptivity assay, it's clustering inside there. There's many ways we use an AI in IVF already. So it's just this is new application of AI for embryo selection. And in my mind, the IVF lab for the future. I know a lot of embryologists are gonna hate me for this. I see it as a time, as I call it, lights out lab. It's basically lab with minimal human interaction, as I see it in the future. It's going to be black box where you put input your eggs or sperm, and you get output certain 1 or 2 embryos for the transfer. This is it. I don't think we train embryologists as much as we can. It takes a long time, but there's human limits. So I think it's just unavoidable. It's the only way we can improve is just using this new tools that are way better than we are. And it's happening actually right now already.
Alejandro?
My take is that one way or another, most people still rely on morphology to make decisions. And just based on the proportion of participants that are willing to try AI, I think that this is just a reflection on the understanding that we have about our limits to rank embryos. We all agree that we're very subjective, that the way that we're doing it is not related to prognosis, and that there must be better ways. And I also agree about the use of time lapse. It's very expensive, it's not accessible. And I'm also pleasantly surprised by the amount of people that is willing to try the non-invasive versions of genetic testing, because at the end, I think that the goal is to get these 360 non-invasive embryo assessment, not to touch the embryo and know which one to transfer.
Absolutely. I think the SPECT media is definitely going to be very synergistic with AI in terms of ranking. So you can rank and you can get a little bit of, a perspective of the embryo in a non-invasive way. So I think that is definitely a good synergy there. Well, we have taken the second poll from the audience. We asked them, maybe John, you can read that for us.
Yes, sir. Yes, sir. So there was 2 questions. The first question was, did this webinar provide you with any helpful information? Resounding 85% said yes, and 15% said somewhat. Second question and final question was, would you like to see a webinar in the future? 100% said yes. So both pretty resounding, statistics in terms of being helpful and for future webinars.
Absolutely, thank you so much. Well, this is just reflecting, the value of the seminar, the information that you guys have provided. I really appreciate your help and your participation. I would like to thank David Silver from Embryonics for providing that information to us and for meeting with us. I would like to thank Dr. Barash for your presentation, and I would like to thank Dr. Chávez Badiola for your inputs. Thank you so much. Next week, we're gonna have another webinar. This time will be focused on patient perspective. Let's send you some outcome in the next few days. So let's meet on Wednesday, 3 p.m. Pacific time next week. Thank you so much for attending. Thanks you guys for participating, and I will see you next week. Thank you.
Thank you.